Okay, participants, let us begin our class. Are you able to see my
Yes,
screen
yes, sir. Yes,
and you are able to hear me also clearly?
yes, sir.
Fine. Now, this sector, energy performance assessment of steel sector, you will find that while studying in book number 2, it's my observation, you will also agree with me, that the book number 2 or even book number 4, we have studied the performance level of boilers and furnaces, whether the furnace is electric furnace, gas furnace, coal furnace, biomass furnace, anything, which are producing heat. And that heat is utilized in different industries for different purposes. But the basic principle of heat content and its distribution is based on common formulas. What is the heat content in, say, for example, flue gas? What parameters you should know? Total heat content are transferred by the gas or extracted from the waste gas is how much? Our universal formula, mCp delta T. Right? Now you are familiar with this formula. M is the mass. It is either in kgs per hour, kgs per day, whatever. Delta T is the temperature difference. That means so many cubic meters of gas has reduced the temperature from say 650 to 400 or 200. So that is the delta T. And what is the Cp? Cp is the specific heat of that particular gas. So multiplication of these three parameters gives you the total heat extracted or total heat added if you are increasing the temperature. Same formula, mCp delta T. How much temperature you have raised. This is common. Whether the temperature is transferred to the steam, it is transferred to the process steam or the flue gases or whatever. So mCp delta T, never forget. Let the industry be anything, fertilizer or steel or cement, paper and pulp. These names are only different. The basic function is the generation of heat, distribution of the heat, and calculating performance level means what? How much positive output is we are getting by putting in some input. So useful output upon input, total input gives you a percentage of efficiency you are getting. Right. Now energy auditor is not only satisfied with calculating the efficiency. When he asks next questions, if suppose the efficiency is only 80%, then the next question is where the 20% has gone. That means there are 20% losses in the input heat. Only 80% is the useful we could get out of the process. Now, if you want to really find out where that 20% has gone, what you have to do is you have to study the process, right? Where the heat is generated in boiler or say furnace, whether there are any inherent losses, whether there is a insulation loss, there is a open door loss, there is a major loss going through the exhaust gases. Particularly, we have seen in coal fire boilers, about 15% is the total loss of the boiler. Boilers has a efficiency of about 85%. That means if 100 units of heat is generated by burning the fuel, 85% units are converted into steam heat. Remaining 15% is carried away by the waste gases. In spite of recovering whatever is the recovery mechanism we are applying, still we could not recover the 15% that goes out of chimney. This is so far as the boiler is concerned. Okay, 1 unit performance we have seen. But this 15%, is it entirely going to the waste gas, or whether it is a excess air supplied to that, whether it is the individual component efficiency that we are losing, isn't it? So you have to find the breakup of the losses. Now, the reason for such small losses in each industry is different. For example, as I said, boiler is known to you. So we will find a boiler, how much is the exhaust gas, how much is the hydrogen in fuel that is burning loss. Then there is a ash percentage that is going on. There is some unburned carbon that is going on into the bottom ash, right? You know all these things because we have studied in paper 2, paper 4 boilers also. Similarly, in steel sector, what are the reasons where such losses are going on? You can read through. See, what I am explaining you is the basic thing which clears our concepts. These paragraphs like introduction, iron making processes, roots, these are simple paragraph and they have very lucidly explained the system, right? Any at your maturity level, you can read and understand. Let us not waste time in that. We will be concentrating on more on concepts. Now there are different processes, routes, the steel making. What is this? Briefly, let us touch for your own. Primary steel route is what? Making the steel using input from iron ore that is coming from mines, iron ore mines. The mining product that is coming out of the fossil that is from the earth surface contains a lot of impurities. There is dust, dirt, there are other elements mixed, there is also organic matter into it, lot of things. It comes in the form of iron ore. Then this iron ore, you have to prepare, you have to use some auxiliary equipments. Prepare means remove the dirt, dust through separation methods, mechanical separation, dry methods. Then whatever purified iron, purified externally, is given to the blast furnace. Now, furnace means there is some heat source. That heat source is given by coal. Now, here you will find it's not the only the coal because we have seen in pulverized boilers, we have used coal and we have ground it to a very fine powder. Here, coal is not directly used in blast furnace because why? The ash contained in coal, the moisture contained in coal. You know the proximate analysis parameters, volatile matter, ash, carbon, and all that. So we are interested only in carbon, not in other components. So in the coke oven, what we do, we put in coal and remove other components. Only pure carbon should go to blast furnace. Why? Because if the coal goes directly, the other contaminating elements in coal will make your steel quality poor. It will have a hell of a problem to remove all the ash and then the volatile matter and other ingredients from the final iron that is melted down. Okay, you got the reasoning only. Okay. So coal is going to first coke oven. Coke oven reduces, that raises the temperature of coal to such an extent that all the volatile matter, ash, everything is removed. Now, this combustion in coke oven or the atmosphere in coke oven is without the existence of oxygen. That means if oxygen is there, the coal will burn here itself and create a lot of heat. No, we want to heat to be preserved for blast furnace. So only the oxygen absence atmosphere. What is the word for that exactly? Let me see. Coke oven. You can read through the anaerobic or something. Some word is that. Now I forget. Okay, and you can read that. So
anaerobic.
anaerobic, correct. So anaerobic condition is there in coal oven and only carbon is going, C is going here. But when C is going, the basic elements like sulfur or some other elements, they are still not removed in anaerobic. No, it goes to blast furnace. And the other reagent, no, which separates the impurities like sulfur and other thing, limestone has that property. So limestone is added, coke is added, and iron ore is added. These three components are added in blast furnace. Why it is called blast? Because a high pressure air supply is given to it like a blast. Very high pressure air, large blowers are here. These blowers will provide the sufficient oxygen level and a very high temperature heat is created in blast furnace. The actual reactions of the heat we will see down. The output of the blast furnace is pig iron, that is the most impure form of iron. This BOF, HOF that you can read through, it's very simple. So the oxygen further added and purified in these two type of furnaces where input is pig iron. But pig iron which is generated from the original iron ore is going to this furnace along with the scraps. No, you all metallic furnaces mostly effectively use the scrap as a recycling process. That means all iron components and different form of useless materials, which is only their properties only they are metals. So the iron as a metal in any form, which is useless, rusted, whatever, that scrap along with this pig iron is fed for purification in these two furnaces. These two furnaces, what they produce is the primary steel. Primary steel means in the form of ingots. The correct word is ingots. That means just like the wooden sleepers, no, large rectangular, long cylindric type or the rectangular type. These are produced in the form of primary steel. Now, primary steel as it is cannot be used in the industry. What we need is we need rods, we need flat plates, we need chains or something or thin wires of this thing steel, many uses of steel. So, primary steel is the raw material for all these other. So, either primary steel itself is marketed or it is taken by other pharmaceutical, I mean the furnace industries for say rolling mills or for say other purposes where the structural steel is manufactured. So the casting, the ingots, etc. This goes to hot rolling, profile, strips, wires. In the hot rolling process, it goes to various steel product. Then after hot rolling, it goes to cold reading when you want to make the specific type of pipe sizes and different thicknesses. Then comes the polishing and finishing, and then this goes to the market. So here one route is directly from the iron ore from the mines. Second route is purely for the scrap utilization. This scrap utilization either can be given along with the pig iron to different furnaces, melted and then clarified, purified and made primary steel, or it can otherwise also be done in a very large electric arc furnaces. Here there is no question of ore. So coal or coke is not required here. Here electric arc furnace is producing heat by consumption of electricity. You know the electricity and heat relationship. 1 kWh generates 860 kilocalories of heat. So we use very large furnaces in megawatt capacities. And these furnaces are very large, like a pot boiling. and in that all the scrap materials are put in. They are melted here. Since scrap is already purified form of metal once, further purification, whatever is, not much more, is done in electric arc furnaces, melted and then casted into different forms. Now, casting of this steel along with all these are identical on the same level he has shown. Whatever is the primary steel casting converted into big chunks of iron, same chunks can be produced from the furnace arc furnaces. And both these steels can be used for hot rolling, cold rolling, and then finished products. Right. Now, what is the third? It is direct reduction route. That means iron ore, instead of going to primary steel route, that means to blast furnaces, it goes direct reduction shafts. Now, this direct reduction shaft is a latest technology wherein all this dirty business is avoided. The iron ore, albeit, has to go through preparation method. The prepared iron ore along with the fuels. Now, fuels used here are again carbon rich, which are again anaerobic process takes place here. Reduction of other elements is taken out and converted into sponge iron. Now this sponge iron is on the same level of the irons made here. Sponge iron here is same equivalent to electric furnace inputs or the BOF, OHF inputs. And then it follows the same route, steel and then rolling. So it is only the route taken by different industries. One industry uses electric arc furnaces and uses scrap as the raw material. Here it is directly the iron ore, coal, limestone and removing the impurities. Here iron ore and the fuels are such plus some additions that will give you direct reduction shaft. The energy consumption in all these three routes is different. Losses are also different and peculiar to the particular industry. Recovery methods are also, heat recovery methods are different. So in steel industry, what we want to learn in this chapter is basically know that steel can be made in three different routes. They have got their own peculiarities, losses, efficiency levels, and the plus and minus. That means sometimes if you want to further purify, you want to, suppose you have to make a molybdenum steel, manganese steel. Now, there you are putting some additions into the steel and they are used for special purposes. For example, turbine steel, right? It's a peculiar steel, very costly. Similarly, the generator outer cases or the transformer core steels, they require peculiarities of different routes. So let us not go into the much detail. It's a vast universe of steel making. So let us read primary steel. What is primary steel process? Production of coal and sinter or pellets from the iron fines. This is a material preparation. Reduction of iron ore in blast furnace or iron making fires. Processing of molten iron to produce steel. And steel forming. Forming means making different shapes. Whether it is triangular, whether it is rail beams or it is the poles, electric poles you want to generate or the tower material, whatever. Steel forming and finishing. Now, here again, this is a block diagram telling you how the blast furnace particularly, first route. This is iron ore, this is limestone, these are put in into blast furnace. Coal directly is not put in here. Coal is passing through coke ovens. Impurity is going out. Only the carbon component goes to blast furnace. And then the sinter plant. What is sinter plant? The iron ore many times goes to another process like called sintering. This also removes the volatile matter and the impurities out of it. Right. Then the output of this, I will give a detailed figure here. Where is that? So that we can understand. Yeah, this is blast furnace. Look at here. The iron ore, limestone and coke, they are put in here at the top of furnace. The combustion takes place here. This is a blast furnace outer shell. This is a hot air that is supplied for combustion. It's a ring all around. It's a circular furnace like a cylinder. All around is the pipe carrying a very high pressure hot air. It is blown through these pipes. You are following now what I am pointing out in the figure. Hello,
Yes, sir.
response.
Yeah. Yeah, yeah. We
Ah,
are seeing you, sir. Yeah.
yeah. So this is blasted through this bottom. The air travels upward, creating a very high temperature zone here. Now in this zone, whatever material is falling from top, that is the iron ore, limestone and coke. Now remember, this is not a continuous flow. There is a capacity of each blast furnace, how many tons you can feed in. Once to the level required, it is feeding, this feeding is stopped. This triangular cover immediately, so long as the flow is going on, it is allowing the material to flow. Flow is stopped, it gets locked. It does not allow anything. Then this material, like a boiling pot, removes all the impurities. The carbon burns from the coke, generates heat, C plus O2, CO2 for perfect combustion. You know the jargon, fuel combustions we have seen. Limestone acts as a remover of the impurities. As a result, what happens? The molten iron trickles down through the entire this thing. Iron being gravitically very heavy, it settles at the bottom. This portion is the slag. Slag means all the impurities floating on the surface of the molten steel. Now, this slag is a surface of impurities. No, it may also contain some metal, but other impurities. So these are separately drained out. This is a slag trolley. If you visit any blast furnace plant, you will find this is a separate slag trolley. This regularly removes. Once they open this door, the slag will come out. Then once slag is removed, then what remains here is the pure metal, iron. That is removed into another trolley, metal trolley. This in the form of molten steel, it is sent to different molds. In the mold, it is poured immediately before it cools down. And the molds are then of different size, maybe cylinders, maybe pipes, or maybe any sort of raw figures which can be further developed into different systematic particular steels. Like this is what the blast furnace is. Now, let us come back to the total plant. Yeah, this is the blast furnace. Now, this blast furnace output either goes to this furnace for
Yes, sir.
refinedness, that means some refined type of steels which are required for plate mills, which are required for some other purposes, CC slabs and all that. And part of it goes to through twin hearths. That is, the hearth means the heating furnace, because what comes out goes to the molds, then molds are cooled down, then in the part of solid materials, this is going to the heated further, made it malleable so that it can be formed into different shapes, and then it passes through a number of rolling mills or different shapes. So this is the shape. Say it is a rectangular shape. It may be a solid round shape. It may be in the form of irregular shapes like stones, right? Then these billets are marketable. you can load into the truck and send it to different steel factories. The persons who are buying these type of shapes convert them into further rolling mills or preparing sheets out of it or the rods and whatnot, wires. These things are further done. This is done by this is merchant mill. That means the vendor who has purchased this, and then the final products like wires, rod, round bars, light structural materials, tower materials. This is one path. This is another, which is a special steels. They add different metals, say like manganese or the molybdenum or other carbon steels. They are prepared and they are sold at a different rates, plates and this thing. This is in short how the steel industry converts the iron ore into heavy structural or rail poles or the rails required for the railway wagons. Right. This is in short, this is what we have understand. This is what is steel industry. Now, real thing which we are going to ask in the question paper, what they will ask you on this. They will not ask you the general description of how steel is made. No, that is too elementary for that. So, a energy auditor, you can, but don't neglect this portion. You read everything, try to understand. Now, this is a coke oven battery. That means what? You are putting coal and that what word you have used, anabolic, I forget. So that process of anabolic quenching car is then taking place here. This is the oven, coke oven. So coke oven battery, why battery? It's a modular form of ovens, number of ovens. And the material flows through it, removes the impurity by using other agents, and then the exhaust of that goes to the quenching tower. That means the heat is removed. The coke in the form of either a plate or the cylindrical portion then is goes to the blast furnace for feeding. These are the cars and guide car and okay, this is all mechanical arrangement. You can in short remember. And the mechanical arrangement and the temperature in coke oven at different places 475, 600, 600, 1100. You just go through for your information. This is the process is sintering. It's a technology for iron ore fines into useful blast furnace burden materials. As I said, iron ore does not come in the form of stones or of the particles. Sometimes it is in the form of dust because any mineral, when you are digging from the earth's surface, it comes in various sizes, right from a very fine particle up to a particle of 5 inch, 6 inch, 10-inch size, right? Assorted. So when you are feeding to the furnace, the solid form, that is 2 inch, 4 inch, can directly be fed. If it is more than that, it's a big stones like 10 inch, 12 inch, 15-inch size, they are to be broken. So primary crusher is required. In the crushing process itself, again there comes out some dust. So what will you do about this dust? Because this dust, if you try to feed in as it will simply blow away along with the air without burning. That will be a tremendous loss. So the entire dust is allowed through a process of sintering. The iron ore fines mean very fine particles. They are converted into blast furnace burden materials. Burden materials mean the material which you are feeding in into the blast furnace. That is the burden means meaning of burden. So you are making them slightly bigger in particle size so that they can be comfortably filled in, used as a feeder material for blast material. That is sintering. And that is why you will find here the word sintering is here. See, output of the sintering plant. That means what the sintering plant is doing? It is aggregating, accumulating all the dust particle into one, sticking together, forming in a small stone size. And that sinter then goes as a feeder material. the composition of sinter is nothing but the same composition. Iron ore, this coke oven, the limestone and this thing. Iron ore out of this thing and iron ore of this and sintering, the material is same. Only it is still in a sizable materials, 2 inch, 3 inch, 4 inch. This is fines converted into the sizable material. That is the only difference. So sintering you can make. Okay, then what we were thinking, sintering, yeah. This is the process of sintering. Means what? The from mining, whatever fines are there, dust, iron ore dust, is in different bunkers. The bunker outlets, that is a very fine dust coming on this conveyor. This conveyor goes to a rotating type of belt. It's a heap it is making. The feeder is making a heap of all the dust particles here. And a fan is blowing the air. So heat is there in this sintering. You can, he has not shown the border, but I will show a rectangular border here. So inside that, the sintering partially melts. The dust partially melts. Impurities burn out because this sintering process is using some oxygen. And this oxygen will burn all the impurities. Only the ore will be melted and a thin layer of metal, molten metal is formed here. This sinter in different parts of a molten metal, they will fall down here. They will fall down in the water. It's a sinter cooler, it's a water tank. So it immediately quenches and a extractor belt will take out the cold sinters on this belt and it goes for the processes further. Now here up to this point it is a hot temperature zone. It is cold sinter. The water gets heated because the very hot sinter is quenched here. That water from sinter cooler gets circulated. But still, if there is some dust remaining here, the heavy particle will be lifted and going to the process, the blast furnace process. Oversize means a larger particle. And very small particle in the form of dust, powder, again goes back to the bunker. It's again reprocessed. So this is what, in short, the return of fines, the fines which could not be converted into sinter, go back. Here is the description of blast furnace. I have already explained. Now, what happens in furnace is the reduction. What do you mean by reduction? Let us understand. The original feeder material that is going into the blast furnace is a mixture of 3Fe2O3. You already know the elementary chemistry. So the molecule formulas you know, plus CO. Now when the reaction in the heat takes place, it gets converted CO2. That means this CO gains one oxygen. And this 3Fe2 is 2Fe3 and O3 goes O4. This happens at a lower temperature. Now this lower temperature zone in a blast furnace is the upper zone is low temperature, isn't it? Because here the fire is working. This is a maximum temperature zone where the metal gets melted. How when the gases go up, the gases get cooled down till they are exhausted from the blast furnace. So in this zone where the minimum temperature is around 400, this first process takes place. Second process at 600 is Fe3O4. From where we have got it? It's Fe3O4 plus CO gives you CO2 plus 3FeO. And the third and the last process which takes place at about 700 degrees centigrade is APO, that is iron oxide plus carbon monoxide is equal to CO2 plus AP. This O is reduced and going to CO2. So here the pure AP is extracted. This process is also again described as APO plus C is equal to CO plus AP. From where the C has come? The C sometimes is injected separately. If not, then whatever coke we are putting in, coke is direct carbon, and this carbon incomplete combustion produces CO. This CO is the reducing gas. It is responsible for removing the oxygen from the iron oxide that is present naturally. So in three stages, the iron oxide is removed, the hydrogen is removed, I mean oxygen is removed from this oxide and a pure form of AP. Finally, this AP melts down at the bottom of the furnace. CO goes away along with the gases. Now, as an energy auditor, I am interested what is the exhaust temperature of this gas going out. Is it 700? If it is 700, it contains lot of heat. Can I use this? Because unless I use this heat, my furnace efficiency or performance will not improve. Secondly, there are other chances of heat loss. One is, of course, the cover. The enclosure of this blast furnace should be insulated. Otherwise, lot of heat will percolate or it will radiate to the atmosphere, right? Thirdly, if I can give a very hot air, if I can preheat the air and give to the furnace, it will add to my efficiency because we preheated air helps. For preheating this air, can I use these gases which are already at 700 degrees centigrade? It's a very high temperature. Can I use this temperature to preheat the air? Then naturally you will of course require a heat exchanger, air to flue gas. And then you will have to tell me the performance of that exchanger. You know the heat exchangers like anything. It may be water heat exchanger, it may be air heat exchanger, gas heat exchanger, anything. So you understand the sources. One is the wastage going through this, heat input through hot air also, insulation quality of this particular thing, and then finally when the molten metal goes out, we are not allowing this molten metal to cool down unnecessarily. So when you are carrying it through the trolleys are to be heavily insulated so that the metal inside does not lose heat and solidifies. It should not be solidified, otherwise it will not flow into the mold and will not go through all the nooks and corners of that mold to form a correct size of product. Got it? Now, from where this heat generated? This is C plus O2 is equal to, this is a complete combustion formula, isn't it? We have seen in fuel combustion chapter. Carbon, when oxidizes, that means carbon plus CO2, they form CO2 and exothermic process gives you a lot of heat. This CO2 is the product of complete combustion. You cannot use CO2 for any other reaction because this is a complete compound. If it is CO, yes, it reduces, it always attracts oxygen from some other. So CO we treat as a incomplete combustion, whereas CO2 is a complete combustion. Now, when incomplete combustion takes place, what happens? CO2 plus C. Some C is unburned. That gives you twice CO2. This is a reducing gas. That is what happens in all these stages. From where this CO has come. See the CO. All this CO indicates a reducing gas. That means it is incomplete, insufficient oxygen. Now, this insufficient oxygen in this process is purposely given for it should have a effect of taking the oxygen from the iron oxides. That is what the blast furnace is doing. Okay, now we have seen this. Read through. The explanation is very nicely given here. Basic oxygen furnace. They will not ask you any question on this. But still, just to clarify your ideas, what is BOF? No, that we have referred this word earlier. And then the continuous casting. There is where is that another OHF? Where is the OHF? You should repeatedly refer this book always. Find out. Yeah. This basic oxygen furnace. And where is the another thing?
Open hearth furnace.
Huh?
OHF.
Open
Open hearth
hearth furnace, right?
OHF.
Yes. OHF is open hearth and this is basic oxygen. Two different methods of preparing the steel for final product. Right. So where we were. Basic oxygen and open hearth. Now continuous casting. This technique accounts for more than 60% of total liquid steel in the world. What is this technique? Uh, had it been a physical class, I would have drawn a separate diagram. But anyway, you remember this. I will try to explain as it is. When this molten metal is collected into this trolley, and this trolley is then taken on rails to a molding shop where this trolley is tilted. It has the mechanism to tilt in this direction, and the flow of the molten metal from the trolley goes directed to the mold holes, no, in which the metal is to be poured for different molds. The molds are aligned in one single line, and the molds are mounted on a train or a rail, you can say, line. So either both mechanisms are there. Either you can keep this trolley steady at one place and move the entire train of molds slowly moving. So on each mold as it comes before the trolley, it will pour, the mold will go ahead, next mold will come like this. Or alternatively, the molds, if they are too big, very heavy, then they are not on the train, but the trolley is on the train and it goes on pouring. Then the trolley moves and the molds remain stationary. Either of these mechanism. This process is called the continuous molding, pouring, casting, continuous casting. When you pour the metal in the mold, it is called a casting or pouring process. Both the words are identical. So this continuous casting is very useful for a large manufacturing plant. 1 minute. During continuous casting, the liquid steel passes from the pouring ladle. The trolley is called a ladle, depending on the size of the industry, size of the blast furnace. Some blast furnaces are nameplate details as 5-ton blast furnace or say 10-ton blast furnace, depending on size. This ladle many times is not a trolley, but a bucket with a handle both sides. So two employees will physically hold the bucket, carry it to the molding spot, and then pour it into the. This is done basically for small molds. Suppose you want to cast the article, each weighing some 5 kg, 6 kg, 10 kg, like that. In that case, then manually the bucket is lifted and poured into the different molds. Ladle is the name common. The ladle can be of a 5-ton capacity or it can be a 10 kg capacity. It's a ladle. With the exclusion of air via a tundish, that means the mechanism which is tiltable with an adjustable discharge device, into a short water-cooled copper mold. The shape of the mold defines the shape of the steel, of course. This is too fundamental, but you read, you will immediately make the ideas clear. Now, when you are pouring, suppose this is the ladle, the molten metal is collected here, and then it is poured here. Though here are the secondary cooling methods, slabs, standard cutting, straightening rolls, liquid core water supply, mold powder, sub-entry nozzles. These are some typical words used in the steel industry. What this is trying to do is, this is to show that the casting method should be continuous. It can be continued till the temperature of the molten metal in the ladle remains at a pourable temperature. Because after certain temperature drop, the metal will not move, it solidifies. It cannot be poured, it will not move. Therefore, sometimes these ladles are intermittently heated by external gas torches or some other methods to keep the temperature of the metal high for longer periods if the pouring time is longer. Got it? These are simple other methods. This is continuous casting. Rolling and finishing mills. If you have visited any of these mills, see, the slabs and thin slabs of the metal are preheated. That means they are purchased from the retailer, goes to the individual rolling mill. In the rolling mill, they have their rolling mill furnace. They use different fuels again, but mostly they use either furnace oil or the CNG, LNG, or compressed biogas. They heat the metal to such a temperature that it becomes softer. Then this soft portion of the metal is allowed to pass through rollers, different rollers. And then the shape is changed either to plates or the pipes or even simply rods, large rods, cylindrical rods. These are called hot strip mills, which are producing thin plates, hot rolled plates, shield plates. Sometimes they are so thin, they are wound like a cellotape, round bundles. You must have seen on the very large trailers going by road, these very heavy bundles of the steel roll mill. Then this is a pickle time and this thing. This is all processes how the different shapes are made. Then there are other rolling mills which are very heavy. They are making such large thickness materials, different sizes of channel sections, T sections, I sections, H sections, only the corners 90 degrees. And then there are the wires, which has got a multiple purpose, either in creating a cement concrete slab or some tower, column for that. So this is rolling and finishing. Now let us come to the important portion. That is energy consumption. Iron and steel industry in India is highly energy intensive. Major industry inputs in the sector are coking coal, non-coking coal, coke, and electricity. The specific energy consumption in Indian steel plants is quite high. It ranges between 6.17 gigacalories per ton to 8 gigacalories per ton of crude steel. Crude steel means which is further processed for making into finer finished products. This is the basic input for all finer input products. This is purchased by individual rolling mill owners and then converted into various forms. So to make this crude steel itself, this is the energy consumption. There is variation of specific energy consumption in different steel plants. This is mainly because of different processes quality of coal, type of products produced, and energy efficiency measures adopted by the plant. The details of specific energy consumption by Indian steel plants are given in this table, right? See, the unit is same, gigacalories per ton of crude steel, okay? Same thing. You will find the range here. Bhilai uses 6.5, Durgapur 6.5, Rourkela 7.09, and so on and so on. Maximum is the ISCO steel plant, ISP. Why? Because ISCO is known for making very fine steels of different metallic compositions. As I said, the turbine steel or the, say, any particular molybdenum steel and other specific required qualities of the steel. Therefore, their energy consumption is slightly higher. But all other are within the range of 6.5 to 7. In the zero point 0.5 range, all these three people are doing it. Now, when the industry uses coke, that means how many processes they are doing? Coal converted to coke and then fed along with the limestone into blast furnace. Blast furnace is also one of the inefficient ways of using heat. Using heat by electricity heat is more clean, more stringent quality control can be done, but it is too costly because you are converting coal heat into electricity at the efficiency of 35 to 30%, 30 to 35%. And then that costly heat you are using for. So electric arc furnaces, the production cost is very high compared to blast furnaces, which is a cheaper way of doing it. In the blast furnace, even a poor quality coal you will be able to use because you are converting that coal into coke before it is fed to the blast furnace. Secondly, the slagging is you are separating out, and that slag which is taken out, which floats on the molten metal, is also used as a building material. It is not a waste product. Secondly, blast furnace exhaust gas, which is at very high temperature, we are using it for some bottoming cycle for generating power, which is used in industry itself, right? The major consuming process in iron making are coking, sinter making, and blast furnace. These are the three main sources we have seen. They consume about 61.3% of the total energy used in a steel plant. Obviously, as an energy auditor, I will concentrate the losses occurring in coking, sinter making, and the blast furnace. If I can get a small percentage of improvement in all these three, in totality, my percentage of use can be reduced efficiently. Instead of using 61.3%, I may be using, say, 55% or 57%. Right? So this is the area of concern by energy audit. The slabbing mill, hot strip mill, cold rolling mill, together with other accounts for 36% energy consumption. That means the use in these other activities is quite controlled and smaller in quantity. Normally, energy auditor will always be making target on priority of the bulk consumers where it is being used, right? And there we will try to concentrate our efforts for saving. So, what he has given here, the energy consumed in 10 raised to 6 kilocalories, that is giga calories per ton of crude steel. This is the total energy and this is the percentage. Coking, suppose this is the energy used, which is about 11%. This is tintering, making, blast furnace. So these three processes together, 61.3%. 1 minute. 61.3% in the total energy percentage that is used. 2.2% in the, what is this? Oxygen furnace, which Okay, you can see the long form. Then the
The
slabbing
basic
bill
oxygen.
and all these are 5.4, 12, 11 together is 36. Why such type of analysis is necessary? Because that is the basic need whenever you go to any industry and try to find out why the performance level is more or less. Then you have to take a review of the entire energy consumption by them, who are the bulk guzzlers of energy. On priority wise, you will concentrate on the areas which are bulk consuming the energy, and there you will try to find out the necessities. Now, secondary steel process, for example, electric arc furnaces. I just made a statement that electric arc furnaces are costly because the electric itself is a very costly product of heat energy. So this is a secondary use of the electricity. A size of this dome is prepared. These are the heating rods called graphite electrodes. The power cables are connected. Why graphite? Because it is a bad conductor of electricity and it generates a lot of heat. If you use metal rod is a good conductor of electricity and it will not generate resistance to the electric current. So these quite resistive rods are used, they get heated. But in the process, they reach such a temperatures that many times the rods are eroded. Over a period, you have to change the graphite electrodes. Right. This is the scrap metal they have put. Here they are not using any iron ore. Remember, it is already a steel, but it's a scrap steel. You have only to refine or purify it. So how do you purify? You create a lot of heat here. The entire scrap is melted. The molten metal, the upper portion of slag is taken away. The pure metal at the bottom is then decanted and used for different molds. Got the process? Blast furnace requires a lot of jugglery because so many impure forms are there. Here, the impurities are only limited to metal impurities, and a small portion goes through the slag, and the bulk portion of molten metal is reused for pouring into the molds. This is a process, typical heat cycle. You can read through. Then, when you go for energy balance, we know the correct way of checking the process performance is to draw a mass and energy balance. When mass and energy balance is correctly drawn, we then find out what are the losses and what are the percentage losses. Now, this is a Sankey diagram for a modern EAF shown a furnace. Depending on the melt shop operation, about 60-65% of the total energy is electric. Remaining is the chemical energy arising from the oxidation of elements as carbon, iron, silicon, and the burning of normal gas. Anyway, so here you will find the energy put in is about 60-65% in the electricity form. This is chemical energy. Now you will wonder what is energy, chemical energy. When this electric raises a temperature, the impurities in the steel start burning. And any burning process is exothermic. They also give out some heat. That percentage of heat coming from impurities burning is 35 to 40%. So in the entire process, we have got two heat processes. One heat generated by electricity, another heat generated by the self-ignition or the burning of impurities. Right. What are the products? Useful product is the steel. 53% of this entire heat gets converted into useful product heat. 17% are the cooling losses. The entire cover or envelope of this is to be cooled, water cooled. That water, cooling water, carries away about 70% heat, 17. 20% another bulk heat. goes out as the exhaust gases, waste gases. Then this is a slag loss. 1, 2, 3. 10% heat is carried away by the slag, which is just removed from the floating portion of the liquid or liquid metal, I will say liquid metal, moltable. Now, if you know this area, what you will find, you will have to concentrate on reduction of the losses. Cooling losses, can we recover this heat which is going to the cooling water? Can we recover the heat going to the waste gases? And can we recover the 10% that is carried away by the slag? See, slag ultimately you have to cool down before it is marketed. So recovery method of this 10%, what are the methods? We'll have to find out. The waste gas recovery depends on what is the outlet temperature of these gases. If the temperature is high, the recovery is better. If the temperature is low, it's very difficult to recover a low quality heat. And the cooling losses also, what happens to the cooling water that goes, whether it is allowing all its heat to the atmosphere or can we gainfully recover it. Right. Now this is the energy and material balance for electric furnace. Here, I will not go into each of these parameters. You read. In the problem or example in the exam also, they will not give you such a complicated thing. Mota moti, they will give only these losses. They will also ask some questions on recovery method, the amount of recovery you can achieve, and what are the methodologies. See, here he has given a case example. Heat balance of rotary furnace in secondary steel plant. See, rotary head furnaces. This chimney allowing the exhaust. Here, it's a secondary air fan. This is passing through a recuperator. On waste heat recovery chapter, you have seen what is recuperator, which recovers the heat from the exhaust gases. Now, this is a furnace. The exhaust gas, that is a hot gas coming out of furnace, goes through this recuperator. This is nothing but a heat exchanger. The heat is exchanged along with the incoming air and outgoing gas. This incoming air, which is at the atmospheric temperature, is raised up to 200 degrees centigrade. This 200 degrees centigrade air is given to this furnace for combustion purposes. The molten metal goes out here, and this is the input of raw material. Impure steel you can say, and this is a pure steel, just for convenient purposes. So impure steel weight is 93.5, pure material that is coming up 92 tons. So 1.5 tons, where it has gone? It will be going in the form of slag or some outbalance, you will see. Fuel input, and this is the primary air input, this is secondary air input. It's just, you look at it like a boiler or any other furnace. The activities are same. One fan sucking the flue gas, another is pushing the primary air. This air is supplied for combustion purposes, same in boiler. In coal fire boiler, what we do? We give air to the coal mill, grinding mill, and then the fan lifts the powder, raises its temperature and gives it to the furnace. Same thing it is. He is raising the temperature of the primary air to 200, giving it to the furnace. Primary air is the base air bulk supplied. See, 700 nm cube per hour. Such a large blower, you can say. So he is the basic oxygen supplier to the furnace. This is used for improving the combustion, and this is sucking the whole thing, all these 700 plus this, passing through that and allowing it to go out of chimney. Now, the temperature gradients, if we say, is the duration is given, but normally if the flue gas is having a temperature much higher. He has not given it here. After recuperator, the temperature may be still 675 degrees centigrade. Whether it is after or before, I will have to check. He has not clarified it. So this 670, yeah, it is after. This 675 degrees gas is not directly sent outside. It is given to the reheat boiler. That means this temperature gas is used as a fuel in this. It doesn't burn here, but it will impart its air for water converted into steam. And this is a steam generator. It's a waste to heat boiler. Then outlet of these temperature gases may be hardly 200 or 250 degrees centigrade. Through the ID fan, it will go to the atmosphere. This trial he has taken for 16 hours, he can take. The fuel used here is LHSS, low sulfur heavy stock. It's a thicker material, petroleum product, which is thicker than the furnace oil. It needs preheating before it can flow. So the heater here reduces the viscosity of this product and makes it thinner as a furnace oil, and then it goes to this furnace, right? Okay. Why it is called rotary? Because all the raw material, impure meal, these blocks, they are put in a radial form. The combustion taking place here and there, and this whole platform is rotating. So the impure steel put here, when the rotation completes, by the time it comes here, it is taken out and the fresh material is put here, right? So these are fresh materials heated to the desired extent and then it is taken out at this point. Temperature here is 1300 degrees centigrade. See, so very high temperature. So its waste is also very high. So the example here is 16 hours of rolling. Hydrogen in fuel is 12%. Water content 0.5%. Calorific value of low sulfur heavy stock, that is fuel, is 10,200 kilocalories per kg. Specific gravity of this is so much. Now, since you are used to solving the problem, just tell me what is the significance of giving the specific gravity?
To convert the liter into the kg, because fuel
Yes,
is in the liter.
volume into weight, right? Volume into weight, because the calorific value given is in kgs, that is in weight measure. So if you want to convert volume into kgs, 0.95 is the specific gravity. Specific heat, 0.5. This is also required because mCp delta T, Cp is 0.5 here. Fuel consumption is so many liters. If you want to convert these liters into kgs, you will have to multiply it by 0.95. Then whatever kgs you will get, so many kgs multiplied by the gross calorific value will give you the heat input. Right. Now, theoretical air required for combustion, 14 kg per kg of fuel. Remember, normally if this is not given and you are burning a petroleum like furnace oil or some diesel, you assume this value 14 kg, right? Assume and write there that I have assumed the theoretical required for combustion per kg of fuel is 14 kg. Temperature of fuel before firing, that is atmospheric, or the steel material which is going inside fuel. Not this is fuel, right? That is LHS here. Here, when it goes inside, the temperature is 100 degrees preheated. And temperature of furnace is 1300 degrees centigrade. Let us see what questions he is asking. He has given me all the total material production so much. 92 is the final product, 93.5 is the inlet. Scale loss. What is scale loss? when the metal gets heated, this surface layer of the metal gets separated. Scaling हो जाता है उसको. And those scales are removed. That is a weight loss. So 1.6% of the total weight is the loss. So for 93 tons, 1.6% comes to 1.5. So 93.5 minus 1.5 scale loss is the final production is the 92. This is the scale loss. Specific heat of steel at 30 degrees, 1300 degrees. Why 30 degrees? Because it's the atmospheric temperature. Specific heat of scale that is shaken off, that is about 1.5 tons. It has carried away so much kilocalories per kg. It's a per kg per degree centigrade. The temperature loss in scaling, how will you calculate? 1300 minus 30 multiplied by 1.5 tons means multiplied by 1000 is kgs, and this is the specific heat. Multiply mcp delta T again, right? Heat of steel also given, scale is also given. Heat of transformation of scale, converting impure into pure. So many kgs of Fe. How many kgs they have done? 92. So 92 multiplied by so many kilocalories and again the delta T. Ambient temperature 30, humidity of air, at atomizing air so much quantity, secondary air temperature 200, specific heat of air at 200 is 0.24 against mcp delta T. All you are using the same formula, only the description names are changing. It is the heat loss in scale, heat loss going into the metal, heat loss going into the air, heat loss going into the exhaust gas, and where you need three parameters, mcp delta T, and all your heat calculations are correct. Now, one thing again I will like to remind that when you do any calculations, you write the formula first. It is always better. Write mcp delta T and then put in the values corresponding to that parameter. That will make you online and also your calculations will go correct. And suppose, unfortunately, while calculating in third stage or fourth stage of your calculation, you misspelled something. That is one figure here and there, you make it change. But if you have taken all the units correctly, all as per formula, feed in the figures correctly, you will get almost 80% of mark, even if your answer is wrong. That means you have proceeded correctly. It's a calculation mistake that as your answer is wrong. Got it? So reduction in marks will be 20 to 30%, but 70% you will get. Out of a 10-mark question, you will get 7 marks, even if your answer is wrong. Provided you have systematically shown how you have proceeded with. Or suppose in assuming the specific heat, instead of 0.24, suppose you assume as 0.3 or 0.25 or 0.28. Right there, I assume specific heat so much and then calculate. You are right. Got it? Because ultimately, a energy auditor is not doing the calculation from memory. Whenever he goes to any industry, he refers to books and then taking the data correctly, he go ahead for the calculations. So that much margin this examination keeps in mind, provided you are systematic. But if you don't put any formula, just start doing your calculation, and unfortunately your figures are haywire. No, if your handwriting is bad, the examiner may not find out what you are actually doing, from where you have got this figure, unless you mention the formula and your assumptions. Got it? So there is nothing new in all these examples. See, here he has given this example, making it as complicated as possible. So that by understanding this was example, all other examples you will not miss doing. What he has done, different MCP delta T is different conditions. While calculating the losses, He has calculated losses for steel, losses for scale, right? Then the ambient temperature, that means gases through the air that is going out, oxygen in flue gas. Again, he is asking you to calculate the excess air losses, if any, because he has given you the hydrogen percentage, the moisture percentage. Then he has also given you the door loss in a furnace. He has given area of door opening 1 meter by 1 meter. Factor of radiation, at what radiation factor it is the radiant loss is going. How many doors of this size are to the furnace? You got my point. All this you have learned in each separate chapters of book 2. You have calculated the heat loss through door of a furnace. You have calculated the insulation, economical insulation thicknesses. You have calculated the excess air loss. You have calculated moisture loss. All these things is already done. And this problem is asking you to refer those formulas and arrive at a solution. And luckily for you, all these answers are given here. What you have to do is just put the correct values and just understand why this formula is here. Why for example, says 991. कहाँ से आ गया भाई? Go to the input data, find out from where. When he has taken this thing, T of a billet, kg of air, or the secondary air required for combustion, so much per billet. So these things, when you tally with what is the input data given and what he has presented here, you will understand it. It takes a lot of effort repeatedly without despairing. You will have to continuously go on doing it. And let us not wait till you are satisfied. Yes, this is a correctly solved example and I understand how it is solved. Okay. Then calculation of specific KL formation. This whole thing, pretty big example, but it is very educating, I will tell you. See, radiation loss through A area into hours into area into specific radiation factor plus so much of furnace opening. How many doors? Two doors are there and then the parameters are there. Specific radiation losses. Heat radiation losses through walls. Walls means the insulation, inefficient insulation, I can say. So you refer to book 2, furnaces, which we have calculated the losses through walls. We have also calculated the economic thickness. Here he has not asked you to calculate economic thickness. He just asking you to calculate the wall loss. Whereas all the input parameters are readily given to you and you just put in that parameter. Then wall surface losses, then radiation losses, radiation heat loss through roof of the furnace. It's also given. Roof furnace surface losses are so much. Total radiation loss from the furnace is so much. Total heat output is the input of addition of all these figures. And then he has tabulated the heat balance. This gives you the different heat balances which you have to calculate. Combustion of heat fuel. So many kilocalories per ton. 96.19 is the total heat content, out of which 96.16 is given by the fuel. Sensible heat of the steel output, that means the useful product that is going out of the furnaces with a temperature difference. The initial temperature of the steel, final temperature of the steel, difference MCP delta T gives you output. That means what? See, mota moti, the fuel has put in so much heat, that is 96% of it. Useful heat that has gone out with the final product is 33%. What is the loss? 96 minus 33. Okay, so 63% is the loss in this furnace, heat loss. When you take only the total input to output ratio, if you take that, input heat is the denominator output, useful output heat is the numerator. Then what you get the ratio of efficiency is only this. Right. Now, sensible heat of the fuel so much. Sensible heat, atmosphere, air, this thing atomizing he has not taken. Heat of formation of scaling loss so much. So the total heat given to the furnace is something 607,926. You have to tally it with this. So what is the distribution? So much sensible heat of the scale that has gone out, sensible heat of dry flue gas that is going out, heat loss for formation of water vapor 9.1, heat loss due to formation of water vapor. Water vapor is formed because of two things. One is presence of hydrogen, another is presence of water itself, that is the moisture. Both the values he has given and we have calculated the loss. Then heat taken away by the cooling water is so much. Radiation heat losses are so much. And others unaccounted losses are 5.2 only. So total heat balance gives you out of so much heat input, useful heat output is only so much. And the other are losses. Now you will find the bulk losses 27% is because of the exhaust gas, dry flue gas. Now this dry flue gas heat can be recovered. Yes, it can be recovered. And when the usefulness of this high temperature flue gas is effectively, gainfully employed in some other process, you can improve this performance level of this. And another is the radiation heat loss, 15%. This we can definitely save. How? Because major loss is through the opening and closing of doors. The loss through the walls, loss through the insulation thickness poor, right? This thing. So you can improve here. You can improve the recovery from the 27. So energy auditor should concentrate on larger percentage of losses where he can gainfully achieve 4%, 5%, whatever he can achieve, and then he can calculate the payback period of your scheme suggested and give a proposal to steel. In a steel plant, daily sponge iron production is 500 tons. Sponge iron is further processed in a steel melting shop for production of ingots. Ingots are the bulk raw steel, you can say. The yield from converting sponge iron into ingots is 88%. That means 12% of the iron is lost in converting impure steel into sponge iron. The plant has a coal-fired captive power station to meet the entire power demand of the steel. Okay, base year is so much, current year is so much. Now you are making a energy consumption data comparison. Base year in 11, current year is 12. Sponge iron production capacity 500. Specific coal consumption for sponge iron 1.2. Here they have improved specific coal consumption. They have improved. That means the coal used in this year is less than what it was used in last year. They must have taken some precautions, improvement methods. So instead of 1.2 per ton of sponge iron product, they have used only 1.1. Specific power consumption, this will obviously also go down because you have improved it here. So instead of 120 kWh, 120 units per ton, they have now achieved a production per ton of sponge at 100 kWh. Yield in converting sponge iron into ingot in steel melting shop, yield remains same. Yield means the ratio of output upon input. 12% loss is there. This was there last year also. This was there. Loss in mass and not in heat. Remember, the sponge iron to ingots to sponge iron, the loss was 12% here, 12% here. Now, what he is asking us, specific power consumption in steel melting shop to produce ingots was so much. It has also improved per ton of ingot. Captive power station heat rate 3,500 has reduced to 3,200. Gross calorific value of coal is remain same. Now, what comes to our mind is if the GCV of coal is same, that means you are using the same quality of coal, but you are reducing the consumption of coal. See, specific coal consumption. Same quality of coal, which was required 1.2 tons per ton of production of sponge iron, has now reduced to 1.1. Improvement. That means your overall fuel rate has come down. Obviously, that will reflect in the total heat rate. Since more coal was used, the consumption was so many kilocalories. Now less coal is used, so consumption has come down to 3,200 kilocalories per kcal. Calculate the specific energy consumption of the plant in million kilocalories per ton of finished product for the base year as well as for the year. Now, specific energy consumption means what? How much energy is required per ton of finished product. You got the difference. Now, here he has given specific consumption for steam melting shop and the sponge iron shop. Finally, you have taken ratio. That means you take out a mass energy balance here. Reduction in coal consumption per day in current year compared to the base year of the plant. Mota moti, these are only very simple calculation if you understand the concept. Specific energy consumption for sponge iron was what? 1200 kg into 5000 plus 120 kg 35 multiplied by 35,000 is equal to 6.2 million kilocalories per ton of steel. The process, two processes is described. One is for sponge iron and one into the finished product, specific consumption for ingots. So these two he has compared, he has taken together the specific energy consumption, this into the mass, 5,000 tons, and another process is 3,500. The weighted average he has taken per ton of SI, so many kilocalories. Total energy consumption per span, so much tons into 500 is equal to so many million kilocalories. Actual production considering 88% ton final is 440. Specific energy consumption of ingot. These are all simply put the values and you will get it. There is no need for me to explain to you because you have already understood all these ideas. That was for the year base year 2011. Here it is 2012. Same thing. The left hand
Sir,
side is remains same.
what
Yes.
doubt, sir?
Huh?
The first one, how it has come, sir? 1200 kgs into 5,000. 1200 kgs is 1.2 tons, sir.
Which column or row?
The specific energy consumption for sponge iron.
For base year.
Yes, sir. 1200 kg into 5,000. Specific energy.
For the two values, no? The requirement you read the given data,
Sir.
right? Which is that 500 tons is the sponge iron production,
Yes, sir. 500 tons.
right? And out of which 80%, 88% is converted into that. 500 into 88%, how much it will be? 440,
440.
right? So specific consumption for sponge iron is for 500 tons because that is sponge iron is prepared from the basic iron of 500 tons per day. Then from this 500, you have converted into specific consumption of ingots. So this 88% is the next value. Where it is 440. Yeah, देखा था where.
Otherwise, it is there here. Sir.
Huh. So
Third one,
third one is what?
440 tons, sir. 500 into 0.88. It's again 120 kilowatt hours. Why we put, sir? 120 kilowatt hours into 3,500 for specific energy consumption. So for specific energy consumption, we have put two. We have added two, na, sir. 1200 into 5,000 plus 120 into 3,500.
So that is a total they have taken. Na? Say out of this, where is that?
Sponge iron production. The specific coal consumption, specific power consumption, both we have to add, sir. Power consumption.
You are checking the energy consumption, isn't it?
Specific energy consumption of sponge iron. Oh, yes. Okay, understood, sir. Coal consumption also we have to add. Power consumption also we have to add.
Total together converted into heat units. Remember that.
Heat units. Okay, sir.
Because similar units only you can add or subtract. Different units you can't use.
3,500 kilocalories, sir.
See here, actual production considering 88%, he has given 440 tons here. And these 440 tons he has used here. Plant specific energy consumption for production of finished product is the 440. So many million kilocalories divided by the final 440 gives you an average million kilocalories per ton of finished product. 10.62. Plant specific consumption for production of finished product. What is the similar value in the next year? It is 9.49. Specific energy consumption production. This is again for 440. You got the point. The production level remains same. 500 tons is the raw product, 440 is the finished product, and the energy consumption is in terms of coal as well as the other, whatever the other source. So together converted into kilocalories heat units per ton of heat units is the comparison. That is the specific energy consumption. अपने दिमाग में क्या हो गया है? We know energy means only electrical energy. It is not so. Energy auditor should not make that mistake. Energy is any form of energy.
Heat energy also.
Yeah. So heat is also a form of energy. And when you are comparing heat as well as electricity, take care that all units are in heat energy. Heat is directly in kilocalories. If it is electrical energy you want to convert, multiply by 860 and use it. And denominator is always the per ton, per kg, whatever the value you want to find out, specific energy consumption. Both these calculations are self-explanatory. So reduction in coal consumption kitna ho gaya bhai? Okay, so much and so much, depending on they have given you the calorific value and all that. So again, my advice is go to the problem, try to understand the problem. You will understand. I'm very sure. Only you need to have some effort, very doggedly. You can't just get discouraged by अरे ये कहाँ से आया नहीं मालूम हो रहा. Repeatedly go through that. Okay, so about 5-10 minutes, we will just browse through these questions. What are the raw materials used in pig iron production? Same thing. What is that? Limestone, iron ore, coke, that is going to. Why BOF is preferred to OHS in open hearth furnaces in steel? Description. Actually, all over the world, they are using more and more OHF because it is not energy efficient, but it is very convenient to use all the scrap material into it. Putting scrap into this is bit difficult. Whereas open hearth is readily accepting all types and all sizes of scrap. Therefore, people are changing over to this. You read through description, it is given in that. What are the raw materials used in secondary steel manufacturing? This is just descriptive problems. And luckily, if these problems come as a short answer questions in paper 4, you may get 1 or 2 questions maximum, only one maybe on this particular chapter. So you just read the theory and you will be able to answer that question because there is no calculation involved, no formula required. It is the description that you have to remember and write like any theoretical question. Then L1, L2, all these lengthy or the big numericals. These L1 and L2 may be 5-mark questions. These are 1-mark questions. And N1 is a 20-mark problem. So in L1, which is a small calculation, hardly 1 or 2 steps of calculation. The annealing furnace in a steel plant has the charging door of so much. Don't get confused by this description of the furnace. Annealing furnace, reheating furnace, melting furnace, whatever nonsense. What we are interested in, what is required. If the door size is given, find out the loss through the door. Temperature is so much, ambient temperature is so much, factor of radiation is so much. Find out the heat loss per hour. One step of calculation only. Once you know the formula, how to calculate it, calculate radiation loss through the furnace door. It may be any furnace, any dam, we are not interested. You go to paper book 2, furnace chapter. The formula is there, just put in these 3 values and you get the answer. That is why the question may carry only 5 marks. But they are assured, once you know the formula, you put in rightly. What some students do, I don't know how that. What they have done, paper 4 being a open book exam, all the formulae which are not there in paper 4, in corresponding chapters, they have put it by writing in that chapter page itself, book page. So when you refer the book, if the particular formula is not there in book 4, but the corresponding boiler chapter in paper 2 has that formula, at least the formula you know, just referring. And once you know look at the formula, you immediately recall, yes, what values are to be put in. That is also one way people have tried to do the shortcuts who are very poor in memory. They don't remember. The actual composition of raw coal oven gas is as this is. So this is a composition of a gas, which is a exhaust gas. Find out composition in dry basis. How do you do that? Paper 2, fuels and combustion, chapter number 1. Go there, you will find the formula and even the solve examples. The composition of blast furnace gas by volume. Here, CO, carbon monoxide, hydrogen, carbon dioxide, and nitrogen. This is the formation. Now, presence of a CO indicates what? Incomplete combustion, isn't it? We know that. If not, go to again book 2, chapter 1, fuels and combustion. Calculate stoichiometric air for combustion. That means what? This is a incomplete combustion. So you need to give correct, calculate the air. That means if you want to convert this CO into CO2, how much oxygen is required? Want to convert H2 into water vapor, H2O, right? How much oxygen will be required? CO2, you cannot do anything. This will remain. N2 is also a neutral. So you have to concentrate where the oxygen requirement of CO2 and H2 to H2O. If that quantity of oxygen you calculate, then air contains 21% of oxygen. So if this requirement is 21, then 100 units of air you will require. So calculate the stoichiometric air, how much will be required. Calculate the gross calorific value of the calorific value gas in kilocalories per nm cube. How will you calculate? Whole thing is depending on formula and these are given. So this entire question is on book 2, chapter 1. Right? You can refer and solve this question. Right? So I have given you at least the ideas how to approach the problems. And therefore, again, I repeat, immaterial of industry, whether it is steel industry, cement industry, paper and pulp and whatnot, fertilizer, anything. So everywhere the heat is used for processes or making electricity or making some other useful use in the process, what you have to use is the MCP delta T, the insulation methods, the technologies which we have referred, fans, blowers, waste heat recovery methods. So once you get a spectrum of all these, then getting 50% marks is, not a big problem. You can easily go through. And this complicated where the performance calculations are more steps in calculation, the formulas in the open book exam will help your memory to put in the correct values which are given in input data. So I think with this we will stop. Okay, should we close?
Yes, sir. Yes, sir.
Stop
Thank
sharing.
you.
Okay. Stop recording.